Welcome to the Explainer. When we see a robot pulling off some crazy complex task, it honestly feels a bit like magic, right? But the truth is, there's absolutely no magic involved. It is just a beautifully logical, interconnected system. So today, we're going to completely shift our perspective. We're tearing down the illusion to demystify the machine and look at exactly how these incredible feats of engineering actually work. Okay, let's dive right into this. Have you ever stopped to wonder what actually transforms a random pile of raw materials, metal, plastic, silicon, into an autonomous entity? Something that can actually make its own decisions? Like, what specifically elevates a standard dumb piece of machinery into a true robot? Well, that is exactly the question we're answering today. Here's our roadmap for the explainer. First, we'll look at the anatomy of a system, then break down the 5 core components. After that, we'll cover the 3 fundamental building blocks and finally wrap up with identifying robot types. All right, Section 1, Anatomy of a System, the big picture. Now, what's really interesting here, and honestly the most important thing to grasp right out of the gate, is that a robot isn't just one solitary thing. It's a highly collaborative system of integrated modules. Notice that continuous flow of information. A task doesn't just magically happen all at once. It actually moves through a controller, which dictates the action, into the actuators, which give it movement, and then finally to a manipulator that physically gets the job done. But check out that bottom loop. While the physical action is going down, sensors are actively feeding error signals right back into an information processing unit. So what you get is this continuous, dynamic feedback loop, constantly tweaking and correcting the robot's actions in real time. Moving right along to Section 2, the 5 core components, building blocks. So what physical parts actually make up that dynamic loop we just talked about? Well, it really helps to think about this in terms of biological anatomy. First step, we've got the controller. This is essentially the robot's brain. Right at its heart is a microprocessor coordinating every single mechanical move. Then we have the sensors, literally the eyes and ears of our machine. These are what let the robot safely navigate its environment, picking up on light, sound, and proximity. But there's also something super cool called proprioceptive sensors. Instead of looking out, these actually look inward to monitor internal factors, stuff like heat and battery life. Fun fact here, humans actually have proprioception too. It's exactly what lets you touch your nose with your eyes closed. Robots are basically using that exact same concept to understand their own internal state. Next up on the anatomy list, we have the muscles and the hands. The actuators act as the muscles. They're directly attached to the structure to literally convert energy into movement. Now, they can be hydraulic or pneumatic, but electric actuators are by far the most common, mainly just because they are so incredibly precise. And then we have the end effectors. These are the hands. This is the part that is actually interacting with the environment to do the physical work. And honestly, depending on the job, an end effector could be anything from a heavy-duty welding torch on a car assembly line to a highly specialized shovel designed to scoop up dirt on the surface of Mars. Of course, literally none of this works without our 5th component, the power supply, the absolute lifeblood of the whole system. This working power could come from batteries, solar power, or pneumatics. But what's really fascinating here is that energy conservation has become such a massive deal in modern robotics. Many of today's robots actually feature smart power-saving modes. They'll automatically minimize their own mechanical motion just to cut down on energy consumption whenever full power isn't absolutely necessary. Kind of like putting your laptop to sleep. So, the crucial point is how all of this comes together in Section 3. 3 fundamental building blocks: mechanical, electronic, and computational. Those 5 physical components we just went through, they don't just act randomly. They're actually systematically categorized into 3 major functional blocks. So let's break down how we conceptually divide the robot. First up, the mechanical block. This is entirely governed by the laws of physics and kinematics. We're talking the physical body, the materials, the joints, and those muscle-like actuators we just discussed. Second is the electronic block. This is your hardware feedback loop. It's where the sensors and microcontrollers live, and they're just constantly reading the surrounding environment. And finally, the third block, computational. This is the realm of software, algorithms, and AI. It's the highest level of the robot's brain, crunching all that data to make complex decisions on the fly. Let's zoom in just a bit on that electronic block. The principles of electronic engineering here are what allow for this constant, completely uninterrupted dialogue between the outside world and the robot's internal hardware. The sensors detect some kind of stimulus, they immediately feed that data to the microcontroller, which processes it, and then instantly commands the actuators to respond. It is a lightning-fast reflex loop, kind of like when you touch a hot stove and pull your hand back without even thinking. But how does the robot actually know what decision to make?
Well, that all goes down in the computational block, which relies on three very specific types of software algorithms. First, you have control algorithms, things like PID or proportional integral derivative controllers, which strictly manage the physical movements. Second, you've got decision-making algorithms. Now, these can range from really simple rule-based trees all the way up to incredibly complex reinforcement learning, basically allowing the robot to decide its next move based on incoming data. And third, perception algorithms. These use heavy-hitting tools like image processing and natural language processing to help the machine actually interpret and understand what its sensors are picking up. Ultimately, this specific block is what makes a system truly autonomous.
Let's move on and see how this all builds into our final section, Section 4, Identifying Robot Types, Design and Action.
We've looked at the universal internal anatomy, right? But how do these exact same building blocks manifest out in the real world when they're assigned totally different tasks? Well, before we look at some cool examples, here's a quick practical guide. If you ever need to identify a specific robot just from a picture or an illustration, you can use these 3 analytical steps. Step 1. Carefully examine the physical details. Really look at the shape, the size, and try to spot any specific end effectors. Step 2. Fire up a search engine with image recognition to find visually similar real-world projects. And step 3. Always check any accompanying references or text for context about its actual purpose. Because in robotics, form always follows function.
For instance, let's take a look at humanoid robots, like Sophia. The whole design intent here is to resemble humans, not just in how they look, but in how they behave. And to pull that off, their mechanical block requires some incredibly complex structures and joints just to mimic basic human flexibility. Plus, they have to rely super heavily on advanced sensors and cutting-edge machine learning algorithms in their computational block so they can safely navigate human environments and seamlessly interact with us.
And this brilliantly illustrates the stark contrast when you completely change the environment. Compare a humanoid on one hand to an unmanned underwater vehicle, or UVV, on the other. To adapt to the literally crushing pressure of the ocean depths, the robot's anatomy has to drastically change. Walking legs? Nope. Those are swapped out for powerful rear thrusters. All those delicate electronic components are now protected by heavy-duty watertight seals. And because visible light is practically non-existent down there, they rely heavily on sonar sensors in their electronic block to map out the pitch-black underwater world. We see a similar kind of extreme adaptation with aerial and ground bots. Aerial robots, which we usually just call drones, absolutely require lightweight, aerodynamic bodies and rotors to give them the lift they need for flight and surveillance. But conversely, look at ground-based mobile robots. They prioritize stability above all else. They use these sturdy, often rectangular bodies equipped with rugged wheels or tracks, which lets them agilely navigate rough terrain and dodge obstacles, all while carrying heavy payloads. Finally, we've got industrial robots. Their native environment is the factory floor, so their design entirely prioritizes extreme precision, doing repetitive tasks flawlessly, and handling insanely heavy loads. Now, whether they take the form of those traditional boxy, angular machines or the sleek, curved modern designs with multiple joints, their mechanical blocks are built strictly for incredible durability and raw power. If there is just one core takeaway you get from this explainer, it's this. No matter how radically different the exterior application is, whether it's flying through the sky, exploring the ocean floor, or literally mimicking human conversation, the internal anatomy remains logically the exact same. The mechanical, electronic, and computational blocks are always there, always working together in that continuous, dynamic system loop. Which leaves us with a really fascinating thought to end on. If the physical body of a robot is basically endlessly adaptable to any environment, and the computational AI algorithms inside of them are currently evolving at an unprecedented rate, what in the world will the autonomous systems of tomorrow look like? As these interconnected building blocks become more and more advanced, the possibilities are genuinely limitless.